Before we dive into the announcement, it's important to understand what particle accelerators are. The Large Hadron Collider, LHC, operated by CERN, is a 17 ring of superconducting magnets and the world's largest and most powerful particle accelerator. It represents the pinnacle of human scientific achievement. In fact, it's so powerful that it can recreate the very conditions of the universe's birth. But could this machine, designed to unlock the secrets of the universe, hold the key to something far more ominous? CERN, founded in 1954, is one of the world's most prestigious research organizations, with 23 member states and thousands of scientists. It's a hub for collaboration and innovation. The LHC is CERN's flagship project, but it's just one part of a vast network of accelerators and experiments. Imagine a racetrack, not for cars or horses, but for subatomic particles in a race against time and space itself. The LHC accelerates protons to nearly the speed of light, sending them on a collision course that mimics the energy of the universe at the time of the Big Bang. The collisions create temperatures 1,000,000 times hotter than the core of the sun. Thousands of magnets guide the protons on their journey, while intricate cooling systems keep the magnets at temperatures colder than outer space. The beams inside the LHC are made to collide at 4 locations around the accelerator ring, corresponding to the positions of 4 particle detectors: Atlas, CMS, ALICE, and LHCb. Each serves a unique purpose, exploring different aspects of particle physics. Together, they act as colossal cameras, capturing snapshots of these collisions. Scientists then sift through the debris, looking for signs of the elusive Higgs boson, also known as the God particle, and other phenomena that offer clues to the universe's fundamental building blocks. By studying the microcosm, we gain insights into the macrocosm. But with every answer comes a new question, and with every discovery, a new challenge. The LHC is not just a scientific instrument. It's a testament to human curiosity and innovation. It embodies our relentless pursuit of knowledge and our desire to understand the fundamental forces that shape our universe. Yet, as we push the boundaries of what we know, we must also consider the ethical and existential questions that arise. What are the risks of probing the unknown? Could our quest for understanding inadvertently unlock forces we cannot control? In the hallowed halls of CERN, where the boundaries of human understanding are constantly pushed, a revelation has emerged that sends a shiver down the spine of even the most seasoned scientists. Brian Cox, a former researcher at CERN and a voice of authority in the world of particle physics, has recently made an announcement that has left the world both fascinated and fearful. Cox's words resonate with haunting clarity. The goal of CERN's Large Hadron Collider is to recreate a mini Big Bang. Yes, you heard that right, a miniature version of the very event that gave birth to our universe. The physicist also went on to explain the implications of this goal, highlighting the LHC's extraordinary potential for making new discoveries. This includes its ability to unlock the secrets of the Higgs boson and explore dark matter, a mysterious substance that makes up a significant portion of the universe. Imagine holding the power of creation in your hands, the ability to conjure the very essence of the universe. It's a tantalizing prospect, but one fraught with danger. The mini Big Bang is not just a theoretical concept. It's a tangible reality within the LHC. The temperatures, the pressures, the raw energy, all mimic the conditions of the universe's infancy. It's like standing at the dawn of time, witnessing the birth of existence itself. But with such power comes responsibility, and the question looms, what if something goes wrong? In fact, something did go terribly wrong. Back in 1978, Russian physicist Anat Borsky experienced a disaster that would forever alter the course of his life. While working on the U-70 synchrotron at the Institute for High Energy Physics in Proino, Russia, a malfunction led to his head accidentally coming into the direct path of a proton beam. The beam, with a force that defies comprehension, passed through his skull, entering the back of his head and exiting through his nose. Borsky's experience was otherworldly. He saw a flash brighter than 1,000 suns but felt no pain. The beam's path left a trail of destruction, burning through tissue and bone. Yet he remained conscious and even walked to the clinic for treatment. The aftermath was both horrifying and fascinating. The beam's path caused localized tissue death, leading to the loss of hearing in one ear and partial facial paralysis. Yet, astonishingly, Borsky's intellectual capabilities remained intact, and he continued his scientific career. This incident is not just a personal tragedy, but a cautionary tale that underscores the immense power and potential danger of particle accelerators. The risks of a particle accelerator like the LHC are not to be taken lightly. The potential for unforeseen reactions, the very fabric of space and time being manipulated, these are not the stuff of science fiction, but real concerns voiced by some in the scientific community. One of the most alarming and captivating concerns associated with the LHC's experiments is the possibility of creating a miniature black hole. Black holes are regions of spacetime where gravity is so strong that not even light can escape. They are cosmic vacuum cleaners, devourers of stars, enigmatic entities that lurk in the shadows of our universe. The idea that the LHC could create such an entity, even on a microscopic scale, is shocking to both the general public and experts alike. Could this black hole grow uncontrollably, swallowing the Earth from within? Though scientists at CERN have assured that any black hole created would be unstable and evaporate almost instantly, the mere possibility has ignited debates, fears, and a sense of awe at the power we wield. It's important to understand how the LHC could create a black hole. It has to do with the fundamental mechanics of particle accelerators. When protons are smashed together at nearly the speed of light, the energy released is so immense that it warps the fabric of spacetime itself. Imagine a trampoline stretched tight, and then a heavy weight is dropped onto it. The fabric bends and curves, and if the weight is heavy enough, it could create a depression so deep that anything nearby would be drawn into it. That's a simplistic metaphor for what could happen in the LHC. In the world of quantum physics, where the rules of the universe are both bizarre and beautiful, there exists a theory that extra dimensions may be hidden within our reality. If these dimensions exist, the LHC's collisions could tap into them, creating a gravitational funnel that forms a microscopic black hole. This enigmatic dance of particles has even caught the attention of some world-famous scientists, particularly the late Stephen Hawking. In his book, he warned of a scenario where the Higgs boson could become unstable at very high energy levels. This instability could lead to a catastrophic vacuum decay, a cosmic event that would not only destroy the Earth but the entire universe itself. The esteemed British cosmologist and astrophysicist Sir Martin Rees also expressed his concerns about the experiments conducted at CERN in his book on the future prospects for humanity. He explored the potential risks associated with particle accelerator experiments, including those at CERN. His words were not merely cautionary. They were tinged with a sense of existential dread. He spoke of a worst-case scenario where an ill-fated experiment could create a condition called vacuum instability. This instability could, in theory, trigger a phase transition that would ripple through the very fabric of spacetime, resulting in a cosmic catastrophe that could engulf the entire universe. Rees's concerns were not limited to theoretical musings. He assigned a probability to these catastrophic outcomes, albeit a low one. But even a minuscule chance, he argued, should give us pause. The stakes are unimaginably high, and the margin for error is razor-thin. The scientists at CERN have calculated the probabilities, run the simulations, and examined the theories to argue for the safety of the LHC. In fact, Brian Cox himself acknowledged the importance of responsible exploration, recognizing that there are widespread fears and concerns surrounding the activities of the LHC. He emphasized that there are rigorous safety measures in place, extensive reviews, and protocols that ensure the LHC's operations are conducted with the utmost care. Cox reassured that the energies involved are well within what the Earth naturally encounters, and the chances of creating a stable black hole are astronomically low. Even if one were created, scientists say it would be so tiny and so unstable that it would evaporate in a flash of energy, a phenomenon predicted by Stephen Hawking known as Hawking radiation. It would be a fleeting moment of cosmic wonder, a glimpse into the abyss, and then gone. Some have gone further, speculating that the LHC's experiments could open a portal to another universe or dimension. This notion, though largely dismissed by the scientific community, has captured the imagination of many and has become a subject of fascination, fear, and even folklore. What lies beyond our reality? Could we inadvertently unleash forces or entities that we do not understand? The idea of opening a portal to hell has even been sensationalized in various media, adding fuel to the fire of uncertainty. But how did this idea come to be, and what does it mean in the context of scientific exploration? The concept of parallel dimensions is not new in physics. String theory, a leading candidate for a unified theory of everything, posits that there may be more than the familiar three dimensions of space and one of time. These extra dimensions could be compactified or hidden from our perception, but they could theoretically be accessed or revealed under extreme conditions. Now, imagine the LHC as a cosmic key, unlocking doors that have been sealed since the dawn of time. When protons collide at energies never before achieved on Earth, they could, in theory, create ripples or tears. In the fabric of space-time, could these ruptures open windows to alternate realities, parallel universes, or even a realm of unimaginable darkness? Ultimately, the future of particle physics, the LHC, and CERN's mission will continue to unfold with breathtaking discoveries and unforeseen challenges. However, as with any journey into the unknown, we must tread carefully, balancing the pursuit of knowledge with a deep understanding of the consequences of unlocking the secrets of the universe. The line between scientific progress and existential risk is razor-thin, and the power to shape our fate rests in the hands of those who push the limits of human understanding. What lies ahead remains unknown, but one thing is certain. The discoveries we make will define the course of our future. As the Large Hadron Collider, LHC, continues to push the frontiers of physics, it is vital to consider the broader implications of such cutting-edge research. The LHC not only seeks to answer age-old questions about the universe's origins, but also to delve into the mysteries of phenomena that remain elusive to current scientific understanding. While the goal of uncovering the fundamental particles that govern our reality is central, the deeper, more abstract possibilities also emerge. These are the questions that challenge not only the physicists but also the ethical and philosophical frameworks that guide scientific exploration. One of the most intriguing aspects of the LHC is its potential to reveal the nature of dark matter, the invisible substance that accounts for roughly 85% of the matter in the universe. Although it has never been directly observed, dark matter exerts a gravitational pull on visible matter, leading scientists to theorize that it must exist. The LHC's experiments aim to recreate conditions that could provide clues to the particle interactions that make up dark matter. Yet, despite significant efforts, researchers have yet to pinpoint a dark matter particle, keeping this fundamental mystery alive. If scientists were to make a breakthrough, it would not only revolutionize physics but could alter our understanding of the cosmos itself. The exploration of dark matter is just one piece of the puzzle. The LHC also provides a testing ground for theories of supersymmetry, a concept in particle physics that proposes a relationship between the two basic classes of particles, bosons and fermions. Supersymmetry suggests that for every known particle, there exists a corresponding superpartner particle with different properties. If confirmed, this theory could unify the forces of nature and explain some of the most perplexing questions in physics. However, the lack of direct evidence for supersymmetry so far leaves open the possibility that this idea may not be the key to solving these mysteries. Additionally, the quest for understanding quantum gravity has intensified at CERN. Theories like string theory suggest that gravity and quantum mechanics, two forces that seem incompatible at the macroscopic and microscopic levels, might one day be unified into a single framework. For example, quantum fluctuations near black holes could reveal how gravity behaves on the smallest scales, potentially solving discrepancies between general relativity and quantum mechanics. Achieving this understanding could allow scientists to explain the behavior of spacetime under extreme conditions, like those found in black holes or the early moments of the universe's formation. CERN's experiments also delve into the very fabric of spacetime itself, including the possibility of higher dimensions. In a space as vast and complex as our universe, the notion that additional dimensions beyond the familiar three dimensions of space and one of time could exist is mind-boggling. String theory and other advanced frameworks propose the existence of up to 11 dimensions, with the LHC possibly offering glimpses of their effects during particle collisions. Some scientists believe that these higher dimensions could explain the weakness of gravity compared to the other fundamental forces, or even provide insight into the possibility of parallel universes. Despite these compelling possibilities, there are inherent risks in conducting such high-energy experiments. While physicists maintain that the likelihood of creating an existential catastrophe is minuscule, the act of accelerating particles to nearly the speed of light and smashing them together opens up unknown possibilities. The sheer unpredictability of some of these experiments means that there will always be critics and skeptics. The theoretical creation of black holes, miniature though they may be, underscores the risks inherent in probing the universe's deepest secrets. Some believe that these experiments could alter the very nature of spacetime, creating a new regime where the laws of physics break down, or in a more extreme interpretation, causing irreparable damage to the universe's fabric. While scientists continue to champion the safety of the LHC and their efforts to rigorously vet each experiment, the possibility of unforeseen consequences looms large. Could a tiny black hole grow uncontrollably, or could some quantum fluctuation lead to destabilizing events? While the likelihood remains incredibly low, the very act of exploring these realms represents a unique moment in human history, an unprecedented adventure into the unknown. Moreover, the debate over the LHC's safety and ethics touches on a deeper question. How much knowledge is too much? Should there be limits on scientific experimentation, particularly when the potential for catastrophic outcomes, however unlikely, exists? As we strive to unravel the mysteries of the universe, we must confront not only the physical challenges of scientific exploration, but also the moral implications of playing with the fundamental forces that shape reality.